All right, so we've just finished quiz 4. I don't know, at the rate that we're going, we'll probably get to 8 or 9 by the end of the semester. Please. So homework 6 related to infiltration is due a week from today. We're going to begin talking about infiltration today. We'll have a little bit more on Tuesday's class. It has some Darcy's Law stuff in there that I think probably is pretty familiar to you already, and so you could get an early start on that assignment if you'd like. It's posted on MU Online. More immediately, though, I think probably it's the midterm exam that's on your radar. So the midterm exam, the coverage is going to be everything up to and including class 13. So that's today's lecture and Tuesday's lecture. So infiltration will be covered on the exam. In the previous class, it was asked about the equation sheet, and so what you can do for that is you can prepare a page on the front and back of any formulas, definitions, and constants that you think you'd maybe need during problem solving. But the exam is going to have 2 parts. At the beginning of the exam will be conceptual questions that you have to solve without the use of your equation sheet. So it's just really going to be what's in your mind and what you can rehearse from memory or from understanding. And then the second part of the exam that you can only begin when you're done with the first will be the problem-solving questions. You should bring your computer for the exam. You may need access to Excel and or StormCAD. So that'll be a week from today for the exam. Oh, sure, yeah, HY8, yeah. I haven't written the exam yet, so maybe he just gave me a great idea. Yeah. So basically, everything we've done through the whole semester is fair game. I'm not ruling anything out. All right. So let's talk about infiltration. Let's put it into perspective, though. There's something that the hydrologist needs to give to the hydraulic engineer. You know, some information so that the hydraulic engineer can size the pipes. So what is the hydrologist going to tell the hydraulic engineer? Flow rate. Yeah, so the runoff rate, because there's also runoff volume. But it's the runoff rate, like the timing of runoff, that is most important for sizing of infrastructure, like canals and reservoirs, ponds, conduits. And so determining Q. What we've talked about already is we've talked about where that runoff comes from. It comes from the sky, you know, the moisture in the atmosphere. And we've talked about how the moisture gets into the atmosphere. It gets there through evapotranspiration, evaporation. We've talked a little bit about characterizing the surface of the ground with rational method C values, how increased urbanization and more impervious areas like more roof area, more pavement, more walkways, a reduction in the amount of vegetated space. All of those trends lead to increased impervious area, which increases runoff volumes and runoff flow rates and increases the speed that those peak flow rates arrive. So what we're going to begin talking about now in this kind of like conceptual formula of where the water comes from and where it's going. A big part of predicting runoff is how much of the water that hits the Earth's surface infiltrates rather than runs off. And so C values was a very crude way to estimate that division between infiltration and runoff. Remember where we said maybe a paved surface would have a C value of maybe around 0.95. And of course that could vary depending on the slope. That could vary depending on the intensity of the rainfall. But we had some rough way of estimating the distribution between runoff and infiltration. What we're going to look at now is some of the science behind infiltration so that we have more sophisticated ways of predicting how much water gets down into the subsurface, because we need something better than C values if we're really going to get scientific and make an accurate estimate Q for the hydraulic engineer to start sizing pipes. So let's talk about soil and the different types of soils that water that hits the Earth's surface encounters. On the one end of the spectrum, there are clay particles, And clay particles, as you probably remember from soil mechanics, are very, very small particles, and they have a very strong attraction for water. Because of their small size, they have electrostatic charge. On the outside, there's a negative charge of the clay particle, and that bonds because of the polar nature of water to the water molecule. And so when we look at K values, so the coefficients that describe how quickly water is able to be transmitted through clay, it's very slowly. On the other side of the spectrum are sand particles, and what makes sand and clay particles so different is the size of the grains. Sand particles are much larger than clay particles, many thousand times bigger. And so they may still have a negative charge on the sand particle, but because the ratio of surface area to volume is so much lower than with a clay particle, the net effect of that negative charge on the size of a sand particle is essentially negligible. So soil properties influence the behavior of water because water is passing through that media. What we have to look at is when there's ponding at the surface, how quickly is water going to be infiltrating down into the pores. These pores, the interconnected voids is like a passageway. It's kind of a tunnel that the water is going to be flowing through to get down into the subsurface. And so if you have clay at the surface and water can't penetrate clay very quickly, that means there's going to be a lot more runoff on a relative basis. But if you have a sandy surface, the water can penetrate through sand relatively quickly. It can penetrate through gravel even faster than sand. And so the larger the size of those tubes, the more quickly water can penetrate down into the subsurface. Here is probably a blast from the past where it's an illustration just to emphasize that soil is very rarely just sand or just clay, but usually the subsurface is a mixture of these different soil types. And we can locate, depending on the percentage of sand, silt, and clay, a given soil into these different classifications. And so, for example, if a soil has more than, it looks like about 58% clay, then it would be considered a clay. It could be a sandy clay if it falls in a certain range, but not too much silt and so on. We'll use in the modeling that we do later on, when we start using a program called WMS, we'll use an even cruder approximation of the soil type. Rather than a soil triangle like this, there are different classifications, 4 of them, soil classifications that have letters A, B, C, and D. And those soil classifications are mainly related to the infiltration capacity of water. But the infiltration capacity of water is directly related to where in this spectrum the soil that we're working with falls. So we won't actually do any calculations related to this, but the main point that you should keep in mind is that what we're balancing out with a soil is the attraction that the soil particles have for the water. And if there's a high level of attraction because there's a lot of charge, then the water can't pass through the media as quickly. Some of the parameters that will be more important for us to know about, we'll need a report of certain soil characteristics to be able to predict what happens. So porosity, remember, is looking at, for a certain unit volume of soil, how much pore space there is. And what this shows is the typical bounding range for a variety of different soil types, everything from sands all the way to clay. What's the range of porosity? And what's kind of remarkable, what was a surprise to me when I first started learning about soil characteristics many years ago, is I would have thought that maybe soil had, I would have thought that clay had a lower porosity than sand, because at first the whole charged particle thing didn't really connect for me. When I had a piece of clay in my hand, I thought, well, there just aren't as many pores there. Like there's less void space compared to the solid space, but that's actually not true. There are sands that have a porosity approaching 45% at the top end of the range. And there are clays that have a porosity at the low end of the range of approximately the same porosity. So this huge variation in behavior that we see for the infiltration capacity of clay versus sand isn't dictated by the porosity necessarily. So the amount of voids is about the same for the two. It's due to the charged nature of the particles rather than the porosity. Field capacity is important to us because what it describes is how much moisture is in the soil after draining away the excess. So think of it as if you were dripping dry some soil, not necessarily baking it and heating it and irradiating it with the sun, but just if gravity is allowed to drain the soil after a few days, how much water is still going to be there. And so now this is where we see a more pronounced difference between clay particles and sand particles. And the reason for that difference is the fact that clay has a stronger attraction to the water molecules because of the charged nature of those really small clay, the negative charge on the clay particles compared to the sand has a charge, but just not much of it relative to the volume. So water drains out of sand really quickly. How much water is in the soil before a storm starts is going to affect how much runoff there is. I used a big phrase a while back, antecedent moisture condition. And it was talking about like how recently did it rain before the storm event in question. And you have to consider the last storm and how it went through the watershed before you can really understand the effects of the storm you're analyzing now. And so if you have a watershed with lots of clays where you don't lose much moisture due to draining, then the antecedent moisture condition can have a much more dramatic effect than if your soil type within the watershed is predominantly sands, which drain more quickly. Wilting point is kind of interesting because what it is a description not only of the soil, but also of plants' ability to draw water out of the soil. So water can be thought of, there's a tug of war between the plants that are planted into a soil and the soil itself, because they both want the water. The soil because of that electrostatic attraction between the charged nature of the particles and the polar nature of the molecules, and then the plants want the water so that they can survive. So what this is showing is that you have to have more water in clay for the plants to be able to extract it, because the clay is holding on to it tightly. And so this wilting point is just another way of looking at how tightly clay holds on to water, because you need to have 20% water by volume in order for plants to be able to extract anything. If you have less than that, then the plants are going to wilt, because they can't overcome that suction attraction that the clay has for the water. But in the case of sand, you can have water percentages down below 5% before you begin to see plants wilting. So the type of soil that you've planted different grasses and shrubs and trees into is going to affect the amount of moisture required for them to survive. So that's an interesting one, wilting point. The basic take-home message for all of these is that water moves through sands more easily than it does through clay. And we can see that directly as well with K values. Let's talk about the soil water pressure. Now this is actually a suction that occurs in the unsaturated zone. And you remember that in fluid mechanics we talked about a capillary effect, which is due to surface tension. And in the lab we observed that. We dipped a little glass tube down into a cup of water and we saw the water level rise inside that glass tube. There were a couple of examples that we worked through to calculate the delta H that can occur based on the surface tension constant of water. But the main thing that we saw was that as the diameter of the tube gets smaller, the water will be sucked up higher in the tube. And the reason for that is that, you remember, this is a force balance. The surface tension force is drawing the water up, but the weight of the water above the waterline is what's causing the downward force. And so in the vertical plane, we put those two things into equilibrium, and the weight of the water is decreasing rapidly when you decrease the diameter of that tube, because the weight of the water is related to the volume, which is a function of diameter squared. So if you make the tube smaller, then diameter squared has a pretty big effect compared to the surface tension force, which is just the wetted perimeter, so the outside circumference of the tube multiplied by the surface tension constant. So as you make the tube smaller, yes, you're decreasing the amount of surface tension force up, but you're decreasing the weight even faster. And so that's why progressively smaller diameter tubes makes the water draw up higher and higher and higher. So that effect is important in the subsurface because there is essentially in the soil grains going to be a suction force. And we'll see it in a lot of different ways. But one thing that we can do is we can attach a vacuum gauge to a tube of water and put it into the soil, and the water will be drawn out of that tube. And the vacuum that's generated in this experiment is a representation of how anxious the water is to infiltrate the water. And so this is a physical property that you can measure, and it varies by soil type and it varies by the initial moisture condition. But we can go out into the field and measure this and make some inferences about what kind of soil there is in a watershed by doing this experiment. So here's a measurement of tension on the vertical axis, log transform of tension. On the horizontal axis, increasing saturation. So what you'd expect is that dry soil is going to be very eager to absorb the water from an experiment like this. If the soil is dry, it's going to be sucking the water out of the tube with quite a bit of tension force. And so you have higher tension when you have a low degree of saturation. But then as the water becomes increasingly saturated, there are lower and lower suction forces. And as the proportion of sand increases in the soil, then the surface tension constant decreases. And so at the top of the mountain, the highest value, you have the highest suction forces for clays. But then as you put a loam, a silt fraction into that clay, it decreases, and sand fraction into that, it decreases even further. So think about rain. You know, this is just some experiment. You can stab a tube down into the water, but now think about what if we have raindrops that are coming to this surface. So how does this, the information that we've gathered from an experiment like this, address what happens during a rainstorm? Well, what we can learn is that if you have dry soil, there will be faster infiltration than if you have saturated soil, because there's less suction when you have saturated soil than when the soil is dry. So, I mean, we kind of would have already guessed that, right? We would have guessed what the trend is. But what this does is it quantifies the trend. It tells you the magnitude of a certain amount of saturation is going to have a certain effect on how easily and how quickly the water penetrates. So you can see that this curve is nonlinear. Now it's a logarithmic scale on the vertical axis, so we have to be careful about that. But we can use it to get a sense of the proportional magnitude of the effect.
So is this system in tension because of the surface tension that's pulling the water up and the soil is trying to suck it out? Is that where the tension is coming from?
Good question. This would be a relatively large diameter tube and not necessarily made out of glass. And so the surface tension isn't drawing the water up with any big magnitude. Where the surface tension is actually observed is inside the soil grains. And so it's not just gravity that's sucking the water out of that, out of this tube. It's actually the little voids that's in the soil. It's drawing the water in all directions. It can draw the water up, like we see here in this diagram. But you know, what if it was upside down? Is what we're saying. So the water is still going to get sucked into some small diameter capillary tube, but then it would also have gravity on its side as well. So the surface tension effect, like if we were in space, we could stab, you know, like how blobs of water float around in space. If we had a small diameter tube, we could stab it sideways and the water would go into that tube whatever direction we were stabbing it from. So it's not necessarily the gravity effect that is important in this diagram on the right. It's just that when you have these interconnected voids, that's like a small diameter tube.
Okay.
Like,
I guess my question is the resisting force to the sucking action of
it's the vacuum.
Okay.
Yeah, so, like you've got a tension. Like, yeah, all of that water can't go out of the tube because this vacuum is pulling it up. Good, great question. So the soil is trying to draw the water out, but only so much of that water can exit the tube because it's creating a vacuum. All right, so I need to talk more about the idea of interconnected voids. Like when you look at soil as a hydrologist, what you should be thinking of is that's just a lot of little tubes down underneath the surface. It is a bunch of soil grains stacked on top of each other. But these soil grains are effectively the same thing as if we had a lot of these little small diameter capillary tubes, because the water is having to go through some path downward. And what we could do is we could come up with like an average diameter of that path that the water is taking down as it travels through the subsurface. And so if you have sand with relatively small diameter voids compared to like a gravel, then the water has to flow through a much tighter path than if it's gravel and these big cobbles with large voids, the water can pass through it more quickly. So the unsaturated zone is the area that's above the water table but below the surface. So sometimes it's also called the vadose zone. That just means the zone that air is inside. Sometimes it's called the zone of aeration. When the subsurface is contaminated, different types of pollutants go different places. Some pollutants are very dense, and they'll go to the very bottom of an aquifer until it reaches some sort of a rock or a clay layer. Other types of pollutants, when they're spilled on the land, they'll only penetrate into this zone of aeration. And so, like, the area above the water table has different names depending on whether you're considering it from a contamination standpoint or considering it from the perspective of water movement. So if it's water movement that we're interested in, we'll call it the unsaturated zone, because that means that some of the voids the voids are partially occupied by air. It's not that there's no moisture above the water table. There's still plenty of moisture in the soil above the saturated zone. In the unsaturated zone, it just means some of the voids have water, because think about now this diagram on the whiteboard here. There's soil grains, and in between the grains is air, but there's also some water that's on the outside edge of those grains. So it's a mixture of some air and some water. And that's why in the previous diagram, we were looking at here the porosity. The porosity is how many voids that are there, but the voids can be partially occupied by water and partially occupied by air. It's not just an all or nothing scenario. And that's where capillary rise comes into play. The water there's even more water as you get closer to the surface of the water table. Now, below the water table, there's no more air in the voids. It's just fully saturated with water. But immediately above the water table, there's a little extra water there. The moisture content is a little bit higher because the water has been drawn up from the zone of saturation because of the small interconnected voids. The nature of those is that they act a little bit like capillary tubes. There can also temporarily, on a short-term basis, be more than the average amount of water near the surface. Because when there's a rainfall event, water begins to penetrate down through the matrix of soil, and so the infiltration is the movement of water downward until it eventually reaches the water table. Now, once it reaches the water table, then it may start flowing sideways, because you can have difference in elevations of the water table having to do with, there could be a lake or a stream over here that the water table is flowing towards. There could be a differential infiltration where you have like a lot of clay in one spot, but a lot of gravel at the surface in another, and so there's more infiltration at the gravel spot, and so the water is temporarily perched on one side of the aquifer and flows laterally towards the other. But for now, one of the important things to think about is capillary rise. Now, a little bit more about those voids, the space between soil grains. If all of those voids are fully saturated with water, then the pressure head is going to be 0, meaning that there wouldn't be like any suction with that device. If we stabbed that tube into fully saturated soil, there wouldn't be any driving force trying to get water out of the tube. But the drier the water is, with decreasing water content, so going away from completely saturated towards oven-dried, at this extreme of oven-dried soil, there's going to be a much higher pressure head. That's measured in terms of centimeters of water. So it's a negative pressure, 10 to the 10th, potentially, centimeters of water would be the suction head of that oven-dried soil. Air-dried, not quite as high of a pressure. Now you can see that this is a nonlinear scale along the axis. Remember, the wilting point was that point below which the plants aren't able to extract water from the soil anymore because it's too tightly bound to the soil grain. And so there's a region here that's called the plant available water between the field capacity, which is just draining by gravity, and the wilting point. Hygroscopic water is what I was trying to draw. I wish I had a different color marker, but it's basically a very thin layer of water around the soil grain that, let's see, I'll take, well, I've got blue already. I'll take black.
Or red.
Red. Well, let's do red. Okay, we've got red water, and so there's a very thin layer of water around the outside edge of these soil grains, and it may not even be touching except in a couple of places. And gravity isn't going to remove that thin layer of water. The plants certainly can't extract it. It's just permanently wet, and it's a small fraction of the overall void space. I guess it didn't do that much to make the drawing that excellent. Yeah.
So it's kind of like a water
Thank you, though.
When you dump it all out, there's still like one drop of the
That's a great analogy. Yeah. Yeah, it's going to be even more extreme than that because, a water bottle, the void is pretty large diameter. But the void is pretty small and the particles are pretty small, so the charge is higher on a soil grain. Tightly held. All right, so this cross-sectional view is showing the pressure of water. And here at the water table, the pressure of water is 0. And as you go down through water, of course, pressure increases linearly, and the slope of that line is the gamma of the water. So its hydrostatic equation would predict pressure under the water table. But above the water table, there is a negative pressure. So this started at 0, and that negative pressure above the water table is related to the capacity of the soil to suck water out of a tube. And so in the capillary fringe, which is that area where there's a little bit more water than normal because of the small diameter nature of the soil grains, then the pressure here could be described as linear. But then there is a a curve that varies a little bit in the intermediate zone depending on how long it's been since the latest rainstorm, how deep the root zone is, like depending on the plants that are being that are growing at the surface, that root zone may go as far down as the capillary fringe. So this is just kind of a cross-sectional view to show you that the deeper you get into the soil, the suction generally decreases. And so the rate that water is traveling through the soil slows down. Think about, like, if it starts raining at the surface, at first the water can penetrate very fast because there's a high suction. But then the closer you get to the water table, the suction decreases. And so the speed of the water penetrating downward decreases. So think about during a storm, once it first starts raining, if you're trying to observe the infiltration rate, that may give you a false sense of how quickly the water is going to infiltrate because there's a declining potential rate for infiltration. We got a 10:45, right? Okay. Hard to keep track of time sometimes. Yeah?
So is there a relation with this to phreatic surface? Is that anything to do with the pressure?
I think that is one way of looking at it. I think on the next diagram, when I show, we'll come to one that shows what happens when it starts raining, and I think that's probably the best of them all, because what happens is there's a temporary increase in the water content at the surface, and that wave of water penetrates down through, and the speed of it can be predicted a variety of different ways. Let me just first of all talk about like the lateral movement of the infiltration. If we have a free surface of water, like a stream or a pond or something, then the water that infiltrates from the surface, the water table can be perched, which means it's just a little bit higher on one side than on the other, and so that leads to sideways movement of groundwater flow. And how quickly it infiltrates depends on what kind of soil is at the surface, and in fact the vegetative cover, how much plants there are, and like the nature of the root structure may provide some little conduits for the water to go down into the soil as well. Like if you have, for instance, like clay soil that doesn't have any plants growing at the surface, then the water is going to run off much quicker than if you had a lot of roots like grass growing in a clay soil. Then the water may be better able to penetrate through the clay if you had the grass there kind of like breaking up the uniform nature of the clay. It's kind of like the roots are another route that the water can take to get into the subsurface. The other thing that comes into play here when we talk about the condition of the soil surface is that sometimes through construction, the voids at the top are going to be filled in with dust. And it's the same thing that can happen in the groundwater recharge dams. If I just jump back real quickly to a picture that I took back in the UAE, let me show you one of the main problems that they had with their groundwater recharge dams is that dust is always coming out of the atmosphere. And where was that? Let's do it this way. Yeah. Water doesn't infiltrate very quickly at this location because the desert is a very dusty environment, and the dust particles that settle at the bottom of this when it's dry will clog up the pores. Even if they started with like a nice sandy soil that would be pretty good at infiltrating, the settlement of dust on the surface clogs up those pores, and then the water doesn't infiltrate as fast as it otherwise would. So a similar effect happens in construction, where if you have a piece of construction equipment driving over soil, it can compact the soil, and compacted soil isn't going to absorb water as good as undisturbed soil. So in this slide where it talks about the soil condition, another thing it's talking about is whether it's undisturbed natural soil or whether it's been artificially compacted or somehow had the openings in the soil affected by construction. So water infiltrates through the unsaturated zone and it increases the soil moisture until it reaches the saturated zone, and the groundwater flow can go laterally towards some subsurface outflow potentially. But once it gets into the subsurface, then it's kind of out of the equation for the sizing of infrastructure, because the movement through the subsurface is so much slower than movement over the surface. Like, think about during a rainstorm, the water is going to get to this lake or to this river a lot faster over the surface than it will through the soil. You know, it penetrates through the soil at the speed of maybe centimeters per second at the fastest, like if it's a really coarse gravel. But at the surface, it may be able to travel at meters per second, especially if it's channelized. And so the water speed over the surface is so much faster that once the water gets into the subsurface, it doesn't contribute much to the peaks that we have to worry about for sizing things like channels and pipes. This is kind of a complicated figure that comes out of the text, and I wanted to spend a minute talking about it because it shows the watershed response during an event. So on the horizontal axis, it's the time starting when the rainfall just barely begins at 0. That's the initiation of precipitation at this vertical axis. And then as we move sideways, what it's showing is where is the water at that point in time. So initially, when rainfall just barely begins, what it shows is that, of course, a certain amount of the water is going to be lost to interception and evapotranspiration. So interception is the wetting of trees, it's buildings getting wet. There isn't going to be any water reaching the ground until that's satisfied. And a certain amount of the water maybe is lost to evapotranspiration. But at a certain given time, there's going to be a little bit of water that's beginning to increase the soil moisture storage, but more of it is filling up the surface storage, meaning that puddles have to be filled up. There has to be a little bit of ponding before the water actually begins getting into the soil and increase in the amount of soil moisture. And later on, once the soil moisture increases, then you can see that the groundwater begins moving sideways because there's an increase compared to where it usually is. And even after that, later on is unsaturated flow, and that means the movement of water above the water table. And so you can see as the water table goes up, some of the water may move laterally through the unsaturated zone. Yeah?
So if we had a big storm event, how much would that change like the water table level? Like as the storm goes on, the water table will continue to rise.
That's right. Yeah, it will.
So will you go back to the last slide? If that pond there, if that rose to above the ground surface all the way to the left, that means the water table is above, like at the level of the surface?
It could. And it's possible that on a temporary basis, the pond could go even higher than the water table. And so then, you know, it looks like usually the water is seeping from the subsurface into the pond. But it could reverse, like if the water goes over the surface of the land and fills up the pond really quickly, then the water could be going the opposite direction. It's usually, you know, the movement of water in the water table is much slower than it is outside at the surface. But you're right that the water table can rise dramatically, you know, depending on whether there's a nearby stream or how quickly it's raining and how far the water table already was from the groundwater surface. Just in a couple of hours, the water table may be raised by several feet. All right, so a couple of important terms, and I think that these show up in the list of like vocabulary that you're going to have to be ready to define each of those terms for each chapter before the exam. And you know, most of them are things that we've talked about in class, but there may be a handful of terms there that you'll need to just review the text to understand completely. The zone of saturation is where all of the void spaces are full of water. The zone of aeration can be broken up into a couple of subzones, but essentially that just means that some of the zone of aeration, the voids have air as well as water. The capillary zone is the closest to the water table. The soil water zone is closest to the surface, and the intermediate zone is just in between those two. So this is showing the capillary zone, which is where the surface tension and capillary effects has a higher water content than in most of the rest of the zone of aeration. This is showing the capillary zone. And below the water table, all of the voids are full. And so we could say if we're going to be measuring moisture content with this variable theta, so theta sub s means fully saturated. So at the water table, the voids are fully saturated. What this figure shows is that even above the water table, there's an elevated amount of moisture because of the capillary effect until we get to the typical water table content, the water content for the rest of the zone of aeration. So there's this gradual decrease in the water content, and there's a whole variety of void spaces in the subsurface. Like, remember that if you've got a mixture of sand and gravel and clay, there's going to be some paths from the surface down to the water table that have a relatively large diameter for like the interconnected route to get there. There are going to be some places where there's just a series of tubes that by coincidence or by statistical anomaly have just really small diameter voids. And a series of small diameter interconnected voids is going to have a much higher raise in the moisture content above the water table. So the question is how can we describe the curvature of this and what happens to it during a storm? That surface tension effect is drawing the water up, but it'll also be drawing the water downward when water accumulates at the surface. And the way that we measure that tendency for water to penetrate quickly, remember, is the suction head psi. And that can be measured in terms of centimeters of water of suction. And one of the ways to measure that is with an infiltrometer. An infiltrometer can be as simple as just a ring of metal that you fill water into, and then you measure, like with a stopwatch and a ruler, how quickly the water decreases in height as it penetrates down into the soil. So this cross-sectional view kind of gives you an idea that when the water leaves the infiltrometer ring, it's penetrating downward, but it's also kind of going out sideways a little bit. And so that doesn't give us the best idea of what would happen during a rainfall event, because in a rainfall event, water would be spread evenly over the entire surface. So water wouldn't be going out sideways when it's raining. Water would only be going downward as it rains. So this single ring infiltrometer is not the best for estimating how the soil would actually absorb water. And so to kind of account for that, the double ring infiltrometer says if we have this outer ring of water that's being used to satisfy the sideward movement of water, then the stuff that's in the inner ring is just going to be satisfying the downward movement. So you can measure how quickly the inner ring drops, and from that determine, in the soil, how deeply it penetrated, and this outer ring is just kind of like causing the sideways movement. And so it's a way of isolating the downward effects from the sideways effects, and kind of like a field method for estimating infiltration rate. course, you have to be careful when using this not to scuff up the soil surface. You'd want to, when you're preparing the surface, have it be representative of the conditions everywhere else in the watershed as they actually are. So you'd try and put this into place maybe in several different spots and come up with a weighted average of the infiltration rate to get an idea of really what's going on everywhere in the watershed. If we take a unit volume in the subsurface, then the porosity is the ratio of voids within that total volume. And one of the earlier figures we looked at said that depending on the soil type, porosity kind of varies from about 25% to around 40%. Maybe in clay soils even higher than that, potentially. Soil moisture content is the ratio of water volume to total volume. Now, soil moisture can never go higher than porosity because, if all of the voids are full, then the water can't soak into the soil grains themselves. And so the maximum soil moisture content will be porosity. So the soil moisture varies from 0 up to the porosity. And when you have saturation, then soil moisture content equals porosity. What we'll be quantifying in a couple of the equations we look at is the change in water content during an event. So during a storm, when the water is penetrating down into the soil, it'll go from the initial water content to fully saturated. And so that change from the initial to the saturated moisture content will be delta theta. And then after the soil drains, then it has a residual moisture content of theta sub r. I think that probably effective saturation is something that you have seen before in soil mechanics class. And that is at a certain given point, like with the conditions as they are now, so this water content theta minus the residual water content, so that's in the numerator, and that equates to how much available moisture there is at a given time. So the difference between how much moisture there is now and how much there will be after it drains. So that theta sub r is the residual moisture that really can't be used by plants, can't be extracted by draining. So the available moisture content divided by the effective porosity. So the effective porosity is saying, the voids minus the residual content, it's the amount of water that could be there if it was fully saturated, minusing out the water that has nowhere to go because it's so tightly bound to the water. Of course, Darcy's law is one way of measuring soil characteristics and how easily water moves through a column of soil. And this is the figure that's in your book related to Darcy's law. Figures like this, because I've seen it so many times, it makes sense to me, but for whatever reason, having the column of water sideways makes it a lot easier for me to understand, at least. If we have a reservoir of water and the water is flowing from an upper reservoir to a lower reservoir, then we have some surface area. We'd call that A. And of course, the water is flowing at a certain flow rate Q. And the difference in elevations, so here's the delta H between the two water surfaces. Now, of course, it's the same thing here. It's just the column is vertical instead of horizontally oriented like I've drawn on the board. But then they're also showing that this needs to be a constant head. So on the right side, this little reservoir of water that's connected, they have an overflow and an inflow so that the water level never changes as the water's flowing through the sand. You have a constant head at the inlet and a constant head of water at the outlet, so that you always have the same H values, so it can come into equilibrium, and then you're measuring the flow rate through the soil as it does that. And Darcy's law says that there's some proportionality constant that describes the ratio of the area, the slope of the energy grade line through the soil. So that is the the difference in heights over the length of the soil column that it's passing through, and that this proportionality factor K will tell you what the flow rate through that soil is going to be. And so if K is bigger, that means that you'll have a higher flow rate for a certain driving force. And it's this delta H divided by the length of the soil column that it's flowing through, that's the driving force. It's kind of what's pushing the water through the soil is the difference in elevations. And so here, where we have the higher elevation on the left, the lower elevation on the right, if you have a bigger deflection in H, that'll be a larger driving force and the flow rate will increase. So that's one way to have a big Q, is by having a big delta H. Another way to increase the flow rate would be to have a larger cross-sectional area. But really what speaks to what's going on in the soil is captured by K. And that's going to reflect like the size of the voids. It's going to reflect the charge of the particles. It's going to reflect those properties that are kind of inherent to the type of soil that it is. So hydraulic conductivity has units of length per time, and it's a really important parameter for predicting flow rate. Now, sometimes Darcy's law is expressed differently, like they'll call J the driving force. J would be the difference in elevations divided by the length. And sometimes Darcy's law is expressed in flow per unit area. So lowercase q would turn that into a flux if you are finding out how much flow there is for every unit of cross-sectional area that the water can pass through. So Darcy's flux has this formula. But I usually use the full hydraulic conductivity equation there. Just to refresh our familiarity with Darcy's law, let's finish by doing this example problem. If we have a fine sand, if you look that up in a table of typical hydraulic conductivities, it might tell you have hydraulic conductivity of 3 meters per day. So let's find out what's the flow rate in terms of liters per day. What's the flow rate through a column of soil that's 1 meter long, 25 centimeter diameter, and then where the head differential, delta H, is 35 millimeters. Well, eventually, let's get liters per day. It's going to give us, when you plug in the given values in terms of cubic meters per day, but it's pretty small. So if we multiply that by 1,000, we'll go from cubic meters per day into liters per day. I think we should see it's about 5.15 liters per day. The other time this semester that Darcy's law and K values is going to be really important is when we start talking about well performance. At the end of the semester, we'll spend almost our entire semester dealing with surface hydrology. But towards the end, we'll look at laws that describe when you're trying to pump water out of an aquifer, how much the drawdown in the water table affects the rate of movement towards the aquifer. And so those equations are pretty interesting, and we'll see K values again. So here's where we're heading next time. When we get together on Tuesday next week, we're going to look at methods for predicting how quickly water penetrates down through the soil. So experimentally, you can measure it directly, but you don't always have access to a site. You may have some basic information about the types of soil in a watershed, but maybe you can't actually go out and measure the infiltration. So there's a variety of different methods that empirically try and answer the question, how quickly is water infiltrating, and over time, how does that infiltration rate decrease as the soil voids become progressively more saturated with water. All right, so let's just look at the announcements one last time. Remember that you've got an exam coming up a week from today. That same day, the assignment is finished. It's due. So if you have any questions as you're working on it, please let me know.